Hello all, welcome back to Sri Sai Tech Edu YouTube channel. Read, Lead, Success. I am dealing with the subject Network Analysis and Control Systems. I have already uploaded Module 1 to Module 4, all the topics of the modules in my channel. If you have missed out, please do watch it. And in this Module 5, I have already completed with the Module 1 chapter, all the topics under this and also problems. So please do watch them. And in the second chapter, we have frequency response analysis. Let us see that in this video. Under frequency response analysis, we have only one topic, that is correlation between time and frequency response. Correlation between time and frequency response. That too only for the second order systems. Correlation between time and frequency response. Correlation between time and frequency response for the second order systems. The standard form of the transfer function of a second order system is, from the figure 7.1, is what? Kv by S into tau s plus 1. This is the feedback where it can be written as what? Omega n square by S into S plus 2 zeta omega n. 2 zeta omega n. If you see here 2 zeta omega n. If you see here S plus 2 zeta omega n, S tau plus 1. These are not, these are both similar. Okay, we'll write this second order system in this way or this way also. If you multiply inside, how you can write? S square plus 2 zeta omega n s, s square plus 2 zeta omega n s plus omega n square. How? C of s by r of s need to be done, no? So this omega n square in by s into s plus 2 zeta omega n is what? G of s. And we are left with h of s as minus 1. So we can write in g of s by 1 plus g of s into h of s. If you substitute this as g of s in this equation, then you will get omega n square by s square plus 2 zeta omega n s plus omega n square. Till here we are done. Then the sinusoidal transfer function of the system. The sinusoidal means what? In the place of s, you will substitute j omega with frequency j omega. So C by R of j omega is T of j omega. Transfer function of j omega in omega n square. In the place of s, j omega is substituted j omega whole square plus 2 zeta omega n into j omega plus omega n square. Omega n square. Then dividing the numerator and denominator of equation 7.1 by omega n square. What you will get? You will be left out with 1 by, okay, omega n square. If you do, then j omega square, j omega whole square by omega n square. What you will be left out here is j square will be minus 1. So minus omega by omega n whole square it will become. So this is the 1. Then next you have 2 zeta omega n into j omega. If you divide this with omega n square, what you will be left with? 1 omega n will get cancelled. So 2 zeta omega by omega n into j will be left. You are done with this. Then lastly omega n square by omega n will get 1. So like that you are going to divide the numerator and denominator by omega n square. You will get this. Then putting omega by omega n as what? U. If you substitute like that, then you will get 1 by 1 minus u square plus j2 zeta omega j2 zeta u. It is not zeta, it is xi. j2 xi u. Xi is what? Damping ratio. If you remember in the second order system, j2 xi xi u. Xi, this is xi, this is u. Okay. Then T of j omega is equals to m is equals to what? The transfer function 1 by square root of 1 by u square whole square plus 2 zeta u of whole square. If you again elaborate this and see, you'll get the previous 7.3 equation only. After that, what you can do, the angle of T of j omega will be what? Equals to phi, that is equals to minus tan inverse of 2 xi u by 1 minus u square. 2 xi u by 1 minus u square, you can write the angle. Okay. Then what you have, the steady state output of the system for a sinusoidal input of unit magnitude and variable frequency omega is given by what? C of t is equals to 1 by the same equation into sine omega t minus phi value what you got? This you will substitute. Understanding? The frequency in the terms of magnitude and variable frequency omega, how you will write? This you will substitute sine omega t minus the phi value whatever you are got. Then after this, from the equations m and phi, what you understand is that 7.4 and 7.5, it is seen that when u equals to 0, what you will get? M equals to 1, u equals to 0 and m is equals to 1. M will become 1. Why? Because this is 0, this is 0, we will get 1 by 1, that is m equals to 1. Then phi will be what? 0. When vu is equals to 0, tan inverse of 0 is what? 0. Why? Because tan inverse 0. 0 when you will get tan inverse of tan 0 is 0. So tan and tan inverse cancel, you will get phi equals to 0. In the same way, when u equals to 1, when u equals to 1, m will be what? You will get, when u equals to 1, this becomes 0. You will be left with what? 4 zeta, that is 2 zeta. Root of 4 zeta square you will get as 1 by 2 zeta. And phi will be what? In the place of u, if you put 1, then you will get infinity. Tan 90 is infinity. Again, tan and tan inverse will be cancelled. You will get minus 90. Okay. Then u is tends to infinity. If u tends to infinity, then what you will get? M is 0. Why? Because 1 by infinity is what? 0. So, if you substitute u as infinity here, then tan inverse infinity when you will get? Infinity when you will get? When it is, as it is infinity by 1 minus infinity. 1 minus infinity means what? 1 minus infinity means what? You're subtracting infinity in minus 1. So, infinity is highest. No, infinity by minus infinity. You will get minus. So, tan 180. So, tan 180. Then after this, the magnitude and phase angle characteristics for normalized frequency u for certain values of zeta are shown in 7.2 and 7.2b. See, for certain values of u, it is shown in this figures. That is when xi is 0.707 and xi is 0.707 less than and equals to. How the the angles are, and the normalized frequency with phase angle and the omega r by omega n and magnitude. How frequency response, magnitude characteristics and frequency response phase characteristics can be seen in this diagram. Then the frequency where m has peak value is known as what? Resonant frequency, which has the highest value, peak value. This is called resonant frequency. At this frequency, the slope of the magnitude curve is what? 0. Let omega r be the resonant frequency and ur is equals to omega r by n. This is what? Be the normalized resonant frequency. So dm by du will be what? Dm by du means you need to differentiate this. If you differentiate this, you will get this. That is equals to what? You will get as 0. Then that if you continuously simplify, you will be left with what? Ur is equals to root of 1 minus 2 zeta square. and UR is what? Omega R by omega n. So omega R will be equals to what? You get as what? Omega R by omega n. So you get omega R as this. Substituting this value of UR in equation 7.4, the maximum value of magnitude known as resonant peak MR you will get. If you substitute this UR in the main equation of MR, then you will get this 1 by 2 xi root of 1 minus xi square. Similarly, the phase angle, if you substitute, you will get this. So from equation 7.7 and 7.8, it is seen that xi approaches 0, omega r approaches omega n, and mr approaches infinity. So for 0 less than xi less than 1 by root 2, the resonant frequency always has a value less than omega n, and resonant peak has a value greater than 1. You can get this is the conclusion. Then for xi greater than 1 by root 2 dm by du, the slope of the magnitude curve does not become 0 for any real value of omega. For this range of xi, the magnitude m decreases monotonically from m equals to 1 at u equals to 0 with increasing u as shown in figure 7.2. As u is increasing, see, m decreases monotonically at from m equals to 1 at u equals to 0 with increasing u. As the u is increasing, the m is decreasing, if you see. Okay, it therefore follows for xi is greater than 1 by root 2. 1 by root 2 means 0.707. There is no resonant peak as such as the great value of m equals 1. We can therefore say that for the second order system, the resonant peak MR of its frequency response is indicative of its damping factor xi for 0 less than xi less than 1 by root 2. And the resonant frequency omega r of the frequency response is indicative of its natural frequency for a given xi, and hence indicative of its speed of response. That is what? 4 by theta omega n. Then for omega r of the frequency response could thus be used as a performance indices for a second order system. From the MR versus U graph, we notice that omega is greater than what? Omega r, m decreases monotonically. The frequency at which m has value of 1 by root 2 is of special significance and is called the cutoff frequency. The signal frequencies about cutoff are greatly attenuated in passing through a system. So, for feedback control systems, the range of frequencies over which m is equal to or greater than 1 by root 2 is defined as bandwidth WB. Control systems being low pass filters at 0, m is equals to 1, the bandwidth WB is called the cutoff frequency. Okay, like that. This is just a theory of how these graphs are represented. In general, the bandwidth of a control system indicates the noise filtering characteristics of the system. Also, bandwidth gives a measure of the transient response properties. Expression for bandwidth. That is just a theory which is required for the graph. Then the main thing is here expression for bandwidth. The typical magnitude versus frequency characteristics of a feedback control system of figure 7.3. This is the bandwidth. This is omega r, omega c. This is cutoff, and 0.707 mr. Okay. So m is equals to, you have this value. You know this formula what we have derived from previously. So 1 by root 2 you will get. So this, if you substitute and if you check, you will get finally this. Then ub square will be what? Ub square will be what? You will get, when you simplify, you will get till here. Then as the bandwidth must be positive real quantity, the negative sign in quadratic solution and the negative sign in taking the square root have been discarded. It is discarded. As bandwidth must be a positive, the negative sign is discarded. Then notice that the normalized bandwidth is a function of xi only. The normalized bandwidth UB versus damping ratio xi plot is shown in what? Figure 4. This is damping and this is normalized bandwidth. So the denormalized bandwidth is given by this is the equation. Now considering the step response of the system, the expressions for the damp frequency oscillation omega d and peak overshoot mp for 0 less than or equals to xi less than or equals to 1 are as follows. Omega d will be what? Omega root of 1 minus xi square. MP will be this. So these are the equations you need to remember. Then MR, the resonant frequency of the frequency response, and MP, the peak overshoot of the step. MR is the resonant peak power the frequency response it is, and it is overshoot of the step, peak overshoot. Response for the second order system are plotted here. Then the comparison of MR and MP plots show where that 0 less than xi less than 1 by root 2, the two performance indices are correlated as both are functions of same damping factor. So from this correlation breakdown, we can tell that for xi greater than 1 by root 2, the step response oscillations are well damped and MP is hardly perceptible. So, similarly, the comparison of expressions for the resonant frequency omega r of frequency response and damper frequency of oscillations omega d of step response reveals that there exists a definite correlation between them. The ratio of these two expressions are this. The ratio of both you will get like this, which is also the function of xi and is plotted here. This is also xi and omega r by omega d. This is how it is plotted. This is how it is plotted. So it is further observed from the expression for the omega b, that is equation 7.11, that the bandwidth, a frequency domain concept, is indicative of undamped natural frequency in for a given xi, and therefore indicative of speed response at time domain concept. In time domain concept, what we need to remember is what? Time domain concept, relative stability is measured by parameters such as maximum overshoot and damping ratio. In frequency domain, resonant peak can be used to indicate relative stability. So bandwidth and rise time are inversely proportional to what? In each other. Means as the rise time is increasing, bandwidth decreases. If bandwidth increasing, rise time decreases. Therefore, the larger the bandwidth is, the faster system will respond. If the bandwidth is larger, the faster the system will respond. Increasing omega increases bandwidth. Okay, decreases the rise time. As the bandwidth is increasing, rise time decreases. So bandwidth is directly proportional to omega and TR is inversely proportional to omega n. Increasing xi decreases what? Bandwidth, and increases TR. So bandwidth and MR are directly proportional to each other. Bandwidth and MR, resonant peak, are directly proportional, whereas MR depends only on xi. Larger values of MR corresponds to larger values of maximum overshoot in the step response. So MP also depends on only on xi. So the general effect of adding a 0 to the forward path transfer function is to increase the bandwidth of the closed loop. Nothing but we are increasing the bandwidth. So the effect of adding a pole to the forward path transfer function is to make the closed loop system less stable while decreasing the bandwidth. So by this, the correlation between time and frequency response of a second order system under chapter 2 is done. Only one topic is there under chapter 2. So by this, module 5 chapter 2 is also completed. After this, I'll start with the chapter 3 of module 5 with a new video. For now, I'm stopping the video here. If you see, I'm completed with the first chapter and second chapter also. Now in the next chapter is Bode plots. I will start the video from Bode plots. Thank you from Sri Sai Tech Edu YouTube channel. Read, lead, success. Keep reading.